Okay. All right, so we're adding this to the Mr. Fullerton notes, the Chapter 21 notes. An ideal battery provides, well, first of all, what is an ideal battery? An ideal battery is one with no internal resistance. Okay, one that acts like the default one on our simulator, to where when we have bulbs in parallel, they always get the same voltage. It never drops. Okay, it always is nice and uniform. No internal resistance. It gets a constant voltage. Constant voltage, which we call an electromotive force. Now, electromotive force, sometimes abbreviated EMF, okay, or as we symbolize it with just an epsilon, an electromotive force is what is pushing your electrons along. It is what supplies your voltage. It is an ideal voltage, right? And it does not change. So if they don't tell you anything about an internal resistance, you make the assumption that your circuit has an ideal voltage, and half the time they'll refer to it as an EMF, okay? Or your circuit, just like this one right here, comes with that symbol there instead of a V. All right, they're synonymous. It just means it's not a realistic battery. Now, a realistic battery has some internal resistance. Okay, now, so this one, it was just something like that. Oops, I'm doing the mirror image thing again. With some electromotive force there. A realistic battery has a noticeable internal resistance, has a value for R sub I. And so what we end up with is our ideal voltage is changed. It's as if right next to our ideal battery we put a little internal resistor, R sub I. Half the time they will draw this stuff so that it's inside of some exterior box or exterior shading. Sometimes they will even give it the whole battery shape to where it looks like that. Okay, not necessarily very often, but once in a while it'll show up like that. I don't think I have an example here off to the side on the sample test. Okay, almost never shows up in an AP exam. Almost never shows up in an AP exam. Shows up more in your book than it does in the AP exam. Now, over here we have a terminal voltage. This is what's measured by a voltmeter. Guys, if there's no current running, what will a voltmeter read if my EMF is 24 volts? I put a voltmeter here, and I put a voltmeter here. What's my voltmeter going to read? 24 volts. Because in order for this resistor to steal some of my voltage, it's got to have a current running through it. So my terminal voltage is equal to my idealized voltage, my EMF, minus, well, the voltage that's used up by the internal resistor. Well, that's going to change with current, so I can't just say V sub Ri. That's going to adjust itself every time. So, well, we know what's V is always equal to. We've always got Ohm's law, so it's going to be I times R sub I, the current minus the resistance. Okay? So if there is no current running, then your terminal voltage is your EMF. Okay? So if you actually want to know what your EMF is, you just measure the battery without anything going through. Right? And then when you measure it later on, when it's running through, plus you can measure what the current is, you can figure out what our internal resistance is. Okay? As a matter of fact, I think on tomorrow's more detailed rendition of playing with the circuits, which can be tomorrow or the next day, depending on when people are out for testing. The next 2 days are going to be work days. Okay? You're going to have a more directed, guided physical circuits activity. Okay? And I think this is one of the ones that I want us to track down, is what is the internal resistance of our power supply. Okay, which is easy enough. We just got to get that voltage when we don't have a current. What is the voltage when we do have a current? We measure what that current is. We can figure out what the internal resistance is. Now, when it comes to having a circuit, let's say I've got a circuit. It can be complicated. It can have all kinds of weird stuff going on in it. I've got a battery here. I've got a resistor over here. I've got a resistor on this branch. I've got a resistor here. I've got a resistor here. I've got a resistor here. Whatever. That'd be fun to put together and everything. By the way, as far as game plan win on this one, the first thing I would do is I would collapse these two because they are parallel with nothing else going on in their vicinity. And then that would reduce to, why not? That would reduce once I've collapsed these two. I would have one up here and one down here and one down here. Those two would have collapsed up here into this one. Okay, that's the one that they just collapsed into. As a matter of fact, let's add some labels here because we haven't really walked through one of these. Let's say this is R1, that's R2, here's R3, here's R4, here's R5. This guy up here is now R34 because he's the combination of resistor 3 and resistor 4. This guy is still R2, this guy is still R5, and R1's over there. Okay. At this point, you would combine up R34 with R5. And by the way, if I wanted to actually find a value, R34 is equal to 1 over R3 plus 1 over R4. Okay, because we got to add them in parallel. Okay, loads of fun there. R34 plus 5 turns into, of course, R345, which would, we'll take it over this direction here. All right, so still got that, still got R1 here. Now, I've still got R2 here, R1. Over here we got D2. No, wrong. No, wrong. No. Here we've got R3, 4, 5, which was just the addition of R3 and 4 plus R5 because they're in series. Then I would collapse these two. I'm not going to do every single little step here. Okay. Next step would be to collapse these two, and then I've going to have, which would be in parallel, all right, which with the 1 over R funness. Then I would add R1 to it because it's in series with these ones. Now, when that's all over with, I've got my battery connected to an overall R equivalent here. Thing is, if my battery was realistic, and it had some internal resistance, all I would have done is I would have added right here a resistor, and I would call that R initial, R internal, not initial. So I would have to do one last step. If I knew I had some internal resistance, at the very end I would add R initial to my R equivalent from the rest of the real battery, and from the rest of the real circuit. Okay, that's really, guys, all you got to do is put your R internal right next to the battery, and then it's in series with everybody, because every ounce of current has to go through that internal resistor. Okay.